Now that we have a bunch of the techniques of these sort of counting ideas, whether it's the fundamental counting principle or the generalized fundamental counting principle, or this idea of how to count things when order doesn't matter, rather. Now that we have all these sort of fundamental techniques in our back pocket, let's go ahead and try to answer some examples of how you can use counting problems. All right, so a very simple one would be to ask this question: how many bank PINs, personal identification numbers, are there? And here I'm assuming that that the PINs have 4 digits, and those digits can only be between 0 and 9. So the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right? So what we're going to do here is take the point of view that we are trying to make a PIN, and we're told that it has 4 digits. Right, so these are the 4 digits that are available to us. And for any one of these, we have a number of options. Right, if I write out all the digits that are available to us, those are the digits that are available, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. All right, so we have 10 options. And we've got 4 spaces to fill. So, if you ask yourself, okay, I'm trying to create a PIN, how many choices do I have for the first number in this 4-digit PIN? Well, I've got all 10 numbers available to me. So I have 10 ways that I could make that first decision. All right, now move on to the next number. There is absolutely nothing in this problem that's telling us that we can't repeat numbers or that there has to be some specific structure to this PIN, right? If you want to have the PIN that is 1111, that is technically a perfectly fine PIN. All right, so this second digit in our PIN, we still have the same 10 choices available to us. Third digit, we still have the same 10 choices available. Fourth digit, the same 10 choices available. All right, and to figure out how many ways we could make these this PIN, we need to use the generalized fundamental counting principle and multiply all of these choices, all of these options together. And remember, this is by the generalized fundamental counting principle. I'm using the generalized one because I've got 4 decisions that need to be made here, each with a different number of options. Well, in this case, they're all the same number of options, but you know what I mean. So the generalized fundamental counting principle tells me that I multiply them all together. That's going to be 10 times 10 times 10 times 10. That's 10 to the power of 4, which is a 1 followed by 4 zeros. So that is 10,000 different PINs. All right. So this is one example of a way that you can use these sort of fundamental counting ideas to try and attack a problem like this, which seems like a fairly simple problem. You've got this idea that you're making your debit card more secure by adding a PIN to it. Well, how many PINs are there out there, right? How hard would it be for someone to sort of guess your PIN at random, so to speak? And, using this kind of idea, they would have like a 1 in 10,000 chance of, pulling the needle out of the haystack, so to speak, and getting your exact PIN just from guessing it. All right, so this is why these kinds of counting problems are of interest. All right, so let's move on to a slightly more complicated version of the same problem. How many PINs are there? And here I'm going to use the same established idea that a PIN is something that has 4 positions in it, and every position is a digit between 0 and 9. All right, so how many PINs have no repeated digits? All right, so what I want you to do right now is pause this video, take a few minutes, try to tackle this problem using the same ideas that we just used on this page, right? So write out these 4 slots, one for every position of the pin, and then write down how many choices you have in each slot and use some sort of fundamental counting idea to figure out the total number of options. All right, so do that right now. Pause this video, take a minute, and then resume when you've done that. All right, so hopefully you have worked on this, maybe struggled with it a little bit, tried to figure out how this might go. So I'm going to start the same way I did before. This pin I'm going to view as 4 separate decisions that need to be made. I need to decide on what goes first, what goes second, what goes third, what goes fourth. Now, I have got 10 options, at least initially, right? So for the first number that I choose, I've got 10 options. Now, I have to say initially here because this specifies that there can't be any repeated digits. So for instance, the pin 1021 would not be allowed because it had 2 ones in it. So 1 is a repeated digit. Something more extreme like the pin 4444 would definitely not be allowed because that's entirely repeated digits. Okay? So an example of a pin that would be allowed would be something like 1234. Right? This is a perfectly fine pin in this scenario. So I have to say that we have some number of options initially. All right, so we've got all 10 digits available to us for this first choice that we make. All right, that first number could be anything between 0 and 9. Now, once we do that, we don't have 10 options left. Now, we've taken one of those numbers and we've assigned it to the first position. This means that we can't use that number again. So now, after the first number is assigned, we only have 9 numbers remaining. All right, now we've chosen 2 numbers out of the pool of 10 initially. So we choose one, that leaves us with 9 left. We choose one more, that leaves us with 8 left for the third spot. And we choose one more, and that leaves us with 7 for the last spot. All right, so for these 4 decisions, I have 10 options for the first one, 9 for the second, 8 for the third, 7 for the fourth. Multiplying these all together by the generalized fundamental counting principle, the total number of options will be 10 times 9 times 8 times 7, which is 5,040. I don't just know that, of course. I just used a calculator. All right, so 5,040 options for pins that have no repeated digits. Okay? So let's soup this up even more. How many pins have a 9 in the third position? Right, I'm completely making this up, by the way. Right, this is just a random question that I'm asking. Right, like suppose you happen to know that your friend's pin is going to have a 9 in the third position for whatever reason. And for, again, whatever reason, you are trying to guess your friend's pin, which probably makes you not a great friend. But regardless, you know that your friend has a 9 in the third spot of their pin. Okay, so take a minute. Again, for every one of these problems, the setup's going to be the same. Take a minute, pause this video, see if you can figure out how many options there should be that have a 9 in the third position. Once you've done this, and you either have gotten absolutely nowhere after you've struggled with it, or you have an answer, resume the video. Okay, so attack it the same way. Right, we've got 4 decisions that need to be made for our pin, and we know something very specific, that there is a 9 in the third position. All right, so one of our decisions is already set in stone, okay? So I'm not going to write that 9 where I just put it. I'm just going to, I just wanted to write it there so you knew that there's, a physical 9 in the third spot. But that's where I've been writing the number of decisions that I have to make, right, that I have available to me. So what I'm going to do is write a little 9 below there to remind myself that that thing has to be a 9, okay? Now, for all of the other things, we still have 10 options available, namely all the digits between 0 and 9. Okay, so that means that for this first position, it could be any of 10 things. For this second position, notice there's nothing in this problem telling me that I can't have repeats or anything like that. So for the second one, there are still 10 options available to me. And now here's where you need to be a little bit careful. Because the third number has to be a 9, how many options do you really have for that third spot? Well, it has to be a 9. It can't be anything else. So there's only one option. Right? If it has to be a 9, there's only one possibility. Right? It's like in those examples I was doing before where you have to choose an outfit and you've got a certain number of shirts and a certain number of pants. If you only own one pair of pants, well then that is your one option for what has to go there. Right? This person has to have a 9 in the third position. So there is precisely one option for what can go in the third spot. Fourth spot, unrestrained. It could be absolutely anything. Multiply these all together to get your answer. And again, this is by the generalized fundamental counting principle. This is going to be 10 times 10 times 1 times 10. And that is 10 to the power of 3, which is 1,000 options. Or pins, I guess. Right, we can be very specific now because we're talking about pins. So there are 1,000 pins that have a 9 in the third position. All right, so the 10 options apply to the sort of unrestrained, right, the unconstrained places, which are spots 1, 2, and 4. And then there's only one option for the constrained position, which is a third position that has to be a 9. All told, this leaves you with 1,000 pins. Okay. Now, here is an interesting sort of adaptation, right? Let's say that you know your friend's pin has a 9 in it, but you don't have the benefit of knowing that it's in the third spot. All right, so it's got a 9 somewhere, but you don't know where. How many pins are there that have a 9 somewhere, but you don't know where? All right. Again, I want you to pause the video, go struggle with this, and come back when you're ready. All right. So you want to know how many pins have a 9 in it, but you don't actually know where the 9 is. So now you run into basically an interesting sort of quandary. All right. Let's attack it the same way we just did, right? If we know that there's a 9 in the third position, we know exactly how to do that because we just did that right here. So let's do the exact same sort of logic, right? Let's say that we happen to know the 9 is in the first spot. Right, so if the 9 is first, well then we have our 4 spots. We have our one option for what has to go first because that has to be a 9. And then we've got 10 options for all the rest because they're unrestrained. Generalized fundamental counting principle tells me to multiply all these things together, and I get 1 times 10 to the third, which is, again, 1,000 pins. Okay, so that's if it's in the first spot. But we don't know that it's in the first spot because, again, we don't know where this thing is. All right, so just do the exact same thing again. What happens if it happens second? All right, so if the 9 is second, well, now you have the 9 in the second position. That leaves you with one option for what the second position can be. It has to be a 9. And 10 options everywhere else. All right, so again, generalized fundamental counting principle tells you that you will have 1,000 pins that have the 9 in the second position. The 9 in the third position, I'm not going to write out again. That's this exact procedure that we just did in number 3. And it led to 1,000 pins. All right, so if the 9 is third, we get 1,000 pins. And lastly, if the 9 is fourth, I'm going to write it out, but hopefully you are on to the pattern here that we are going to have 1,000 pins. And again, this is by the generalized fundamental counting principle. We get 1,000. Okay, so we need to answer the full question, right? The full question is, how many pins have a 9, but you don't know where the 9 is? Okay, so you've got options here, all right? It could be first, or it could be second, or it could be third, or it could be fourth. Every one of those options gives you 1,000 different pins. Right, and it's they are necessarily like different pins because what we're really addressing by putting the 9 in these different positions is what I will refer to a lot from now on as a formatting problem. All right, your pin is format dependent, meaning that if your pin is 9000, that is a different pin than if it were 0900. Right? It's got the same digits. The two pins I just said have exactly the same digits. They both have 3 zeros and a 9. But the fact that that 9 is in different spots makes them different pins. All right? So it's just like a password, right? If you jumble up the letters in your password, no website is going to let you on. It's going to tell you that your password is incorrect. All right, so this is a formatting issue. What we're really addressing here is all the different ways that the 9, or this pin, could be formatted, and that's by addressing all the different places that the 9 could be. Right? It could be first, second, third, or fourth. So, the idea here is that the 9 could be first, or second, or third, or fourth, and each one of these options gave us 1,000 pins. So now you have to ask yourself, how do I combine this total pool of pins into the answer that I actually need it to be? And the way that you do this, and here's one thing you want to be careful about, you're connecting by the word or. And when you do that, you want to add these together. All right, if you could think of this, there are lots of ways that you could have this make sense to yourself. I'll let you think about it rather than trying to tell you an exact way to think about it, because I want you to sort of realize this on your own, that adding is the right thing to do here. This leads you to 4,000 pins that contain a 9, but you don't know where the 9 is. All right, let me give you a slightly different way of thinking about it. And this slightly different way of thinking about it is the sort of formatting way. All right, so a formatting approach. It's not how you spell formatting. It's got 2 T's. Otherwise, it would be formating, which sounds like something entirely different. So, formatting approach. The thing I want to do here is ask the question, how many formats are there? And how many pins in each format? All right, the way that this is going to answer the question for us is by, again, using the fundamental counting principle. Because in viewing it this way, what we're really doing is we are breaking down a given pin into two decisions that we have to make. We are going to choose all the digits that are possible that can go into it. That would be how many pins there are in each format. And then we are going to decide on the number of formats that are possible as our second decision. All right, so you're going to decide, or you could do it the other way around if you like. You could decide on a format first, and then you can decide on a pin within that format. Either way, we're viewing this as two decisions that are being made. One is choosing a format, in this case, where that 9 should go, and then choosing a pin within that format. And because this is we're viewing this as two decisions that we're making, if we can figure out how many different formats there are and then how many pins are in each format, the fundamental counting principle says to multiply these together to give us the total number of pins that have a 9 in it, no matter where the 9 is. All right, so this is the idea, and this is my preferred way of solving problems like these. All right, so the number of pins in each format, this is the question that we answered 4 different ways up here. All right, so what we're going to do here is just pretend that we've got any particular format. So for instance, let's go with this one, the 9 first. Well, using the fact that the 9 is first, we came out with 1,000 pins. And just in case you're wondering if it matters which format you choose to make this calculation, notice that we got 1,000 no matter which format we used, right? No matter where the 9 was, we got 1,000 for all of them. Okay, so the number of pins in each format is 1,000. Now the number of formats. All right, how many different places could that 9 be? Well, it could be first. Sorry, that was meant to be green. It could be first. It could be second. It could be third. Or it could be fourth. That's 4 different places that this 9 could appear. In other words, there are 4 ways of formatting a pin that has to have one 9 in it. Or at least one 9 in it. Right, so there's a 4 right there. Fundamental counting principle says to multiply these together. That gives you the 4,000 that we just said we are supposed to have. All right, so 2 different ways of seeing the same thing. Now, they're really saying exactly the same thing because what we're really doing here is just adding up, right? In this approach here, we're adding up how many were in the first format, how many were in the second format, the third format, the fourth format, and then we're just adding up, saying it could have been any one of those 4 formats. All right, so the final answer to this question is 4,000 pins have at least one 9 in them. Okay, how many pins consist of the digits 1, 2, 3, 4? And here I mean all 4 of those digits have to be present. All right, so for example, the pin 1, 2, 3, 4 is an example of one of these. The pin 2, 3, 1, 4 is an example of one of these. The pin 1, 1, 2, 3 is not, because it doesn't have a 4. Okay? So this is what I mean. It's got to have a 1, 2, a 3, and a 4. It's the order that doesn't matter. All right, so how many are there that look like this? Again, pause this video, take a minute, or a few minutes, struggle with this, and come back to the video when you've got some progress. Okay, so we're going to view this the same way we've been viewing all of these. We have decisions to make. right? We've got 4 positions in our pin, and we have 4 options for the first one. It could be either a 1, a 2, a 3, or a 4. So we've got 4 options right there. All right, now, we've chosen one of those numbers to go first. And like I just said right here, we cannot allow the same number to go again. Right? Otherwise, it won't have, it's only 4 numbers long. It can't possibly have 4 different numbers in it if we have a repeat. So, once I choose a number to go first, I knock that number out of my list. That leaves me with 3 options to go second. Now I've knocked 2 numbers out. That leaves me with 2 numbers to go third. And I've got 1 number that has to go last. Generalized fundamental counting principle says to multiply these all together. And I get 4 factorial options. All right, it's 4 times 3 times 2 times 1. This is 24 pins that consist of the numbers 1, 2, 3, and 4. Right, there are 24 of these. And notice this is really saying a very similar thing to what we talked about in the weighted voting theory chapter when we talked about sequential coalitions. Right, this is like asking how many sequential coalitions are there among 4 players. And the only difference when we did that calculation was that there were angled brackets around this to indicate that it was a sequential coalition, but the procedure was identical. All right. How many passwords consist of 6 lowercase letters? All right, so now we are shifting away from pins a little bit toward more complicated things, which are passwords. All right, so it's got 6 lowercase letters. If we want to have some idea for how to do this, right, 1, 2, 3, 4, 5, 6 decisions need to be made to construct this password. You have to decide on a lowercase letter for each one of the 6 spots. Now, how many options do you have for each one of these spots? Well, that's answering the question, how many lowercase letters are there in the English alphabet? And that is 26. Right, there are 26 lowercase letters in the English alphabet, meaning that we have 26 options for the first letter in our password, 26 for the second, 26 for the third, 26 for the fourth, 26 for the fifth, and 26 for the sixth. Right, there are no restrictions on this password at all, other than the fact that they're all lowercase letters. All right, so the generalized fundamental counting principle tells me that the total number of passwords is 26 times itself 6 times. In other words, 26 to the 6th. And now, if you're curious how many that actually is, it is quite a few. All right, it is about 309 million. All right, so there's a few of those. Now, here is where we start to cook with gas. All right, here we have a it's not even very complicated. Here we have a slightly more complicated password format. It's got to have 6 lowercase letters, 1 capital letter, and 2 digits. How many passwords are there that have this? So, I'm not going to answer that in this video. This is going to take some time to develop. But I want you to think about, before you move on to the next one, I want you to think about this issue of formatting. Right, this is really going to be how we're going to attack this question. Right, it's not too hard to count all the different ways we could choose 6 lowercase letters. We just did that. The ways we could choose 1 capital and 2 digits. Right, these are not the hard parts of the problem. The hard parts are figuring out how to account for the different ways that passwords can be formatted. All right, so see the next video for how to do that.